Have you ever stopped to think about what happens to energy when you use it? When you burn gas in your car or just flip on a light switch, where does all that energy actually go? Does it just poof, disappear? Well, it turns out the universe is an incredibly precise bookkeeper. It has a fundamental rule for tracking every single bit of energy, and we call it the first law of thermodynamics. Think of it as the universe's own energy ledger. At its heart, the first law of thermodynamics is a really simple but totally unbreakable accounting rule for all the energy in the cosmos. What it tells us is that for any system you can imagine, the energy that goes in, the energy that comes out, and any energy that's stored inside, well, it all has to perfectly balance. In this ledger, absolutely nothing ever gets lost. Okay, so if we're going to understand this cosmic ledger, we first need to meet the key players. You can think of them as the three main types of transactions you can make. You've got your deposits, your withdrawals, and of course, your account balance. We just call them heat, work, and internal energy. Let's really lean into that accounting analogy. Heat, which we write as delta Q, that's your energy deposit. It's any energy you transfer into the system. Work, or delta W, is your withdrawal. That's the energy the system uses to do something to the outside world, like pushing a piston. And finally, internal energy, delta U, well, that's your account balance, the total energy the system is holding on to at any given time. So what exactly is this account balance, this internal energy? Well, if you could zoom all the way down to the molecular level, it's the sum of all the little bits of energy in there, molecules vibrating, spinning around, and even the energy locked up in their chemical bonds. It's the system's own internal energy savings account. All right, now that we know the key players, let's get to the heart of it. Let's look at the actual equation that balances the books. It's an incredibly simple formula, but it is so powerful. It's what governs all of this universal accounting. And here it is. This is the core of the whole ledger. The equation is just delta U equals delta Q minus delta W. So what does that mean? It means the change in the system's stored energy, the delta U, is simply the heat you put in, your delta Q, minus the work the system does, your delta W. It's just storage equals input minus output. Perfectly balanced every single time. Now, that little formula is really just the mathematical way of saying something you've probably heard a million times. The law of conservation of energy. It's the universe's absolute guarantee that you can't just create energy out of nothing, and you can't make it vanish into thin air. It can only ever change form. All right, enough with the theory for a second. Let's put on our accountant hats and apply this to something you see every day. We're going to balance the energy ledger for a process that seems really simple on the surface, boiling just a single gram of water. So here's what we're going to do. It's super simple. We're going to apply heat to 1 gram of liquid water until it's completely turned into steam. Our job is to be the universe's bookkeeper here and track exactly where every single joule of that heat energy ends up. Okay, time to look at the numbers. Now, to turn 1 gram of water into steam, we have to put in 2,256 joules of heat energy. That's our delta Q, our energy deposit. But here's where things get really wild. Check out the volume change. That tiny little gram of water expands from just 1 cubic centimeter all the way up to over 1,600 cubic centimeters. That massive expansion is the key to everything.
So, where does this work come into play? Well, as that water explodes into steam, it has to physically shove the air in the atmosphere out of the way to make room for itself. That physical act of pushing, that's work. And we can calculate it. We find that work, delta W, by multiplying the atmospheric pressure, P, by how much the volume changed, or delta V.
So let's actually run the numbers. We take the atmospheric pressure, which is about 101,300 pascals, and multiply it by that big change in volume. The result? Our expanding steam did about 169.2 joules of work on the atmosphere. That right there is our delta W, the energy withdrawal from our system.
And now, finally, we can balance the ledger. We just plug our numbers into the formula. Delta U equals delta Q minus delta W. We put in 2,256 joules of heat. The system spent 169.2 joules on work, so we subtract the two, and we find that 2,086.8 joules are left over. That energy didn't just vanish. It was absorbed by the water and became its new, higher internal energy. This chart just makes it crystal clear. Of all the energy we put into the system, a whopping 92.5% of it went straight into increasing the internal energy. Literally, it was used to break the bonds holding the water molecules together as a liquid. Only a tiny little fraction, 7.5%, was actually used for external work. So the big takeaway here is that changing a substance's state is almost entirely an internal energy transaction.
So, what does this all mean in the grand scheme of things? Well, this simple example of boiling water actually reveals some pretty profound rules about how energy works, and it leads us to a really interesting question about the whole process. Yeah, this brings up a really fascinating question. If you have a system that moves from some starting state to some end state, does the specific journey it takes to get there actually change the final energy accounting? And the answer is, well, it's fascinating. It depends on what you're measuring. The change in internal energy, delta U, is what we call a state variable. It only cares about where you start and where you end, not the journey in between. Think of it like hiking up a mountain. Your change in altitude is fixed no matter which trail you take. But heat and work, they are path-dependent. They're like the calories you burn on that hike. A long, winding trail is going to cost you way more energy than a short, steep one, even if you end up at the exact same peak. So let's quickly summarize the key rules we learned from our energy ledger. First, conservation. All the energy gets accounted for, period. It's either stored or used for work. Second, path independence. The change in that internal energy, the delta U, is always the same between two states. And third, application. When something changes phase, like our boiling water, almost all of the energy goes into fighting molecular forces inside the substance. So why does any of this matter? Because this one single law gives us the accounting framework for, well, everything, from the way a car engine works to the simple act of boiling a kettle, all the way up to the huge, complex weather systems that shape our entire planet. The first law is always there, quietly keeping the books in perfect balance. And that leaves us with one last big thought. The first law guarantees that energy is never truly lost, it's only transformed. We just saw that over 90% of the energy we use to boil water was just stored as internal energy in the steam. So what does that mean for the future of technology? What if we could get better at tapping into these huge internal energy changes, capturing and reusing the incredible amounts of energy that are all around us all the time?